We're going to talk new topic related. We're going to talk about number sets today. So the set of all the numbers you've ever dealt with, we could call the set of real numbers. Any number you've ever used ever has been a real number. Today we're going to look at how we can partition that off and divide it up into some useful subsets, smaller sets that are contained in that set of real numbers. To start things off, I'm going to make this really quick because I think there are some people that have some account issues that I want to make sure we're able to address here before the weekend. So we'll make this pretty fast. If we want to look at one way to represent sets, it's with a Venn diagram, okay, or a set diagram, where the big green bubble contained, we didn't do this yesterday, right? Anything like this? Okay, right. The big green bubble contains the set of all possible pets. How about? Inside that big green bubble, that big green set, are some smaller subsets. For example, the set of all cats that are pets would be a smaller subset. Now, the orange set of all cats that are pets is completely inside the green set because all cats are pets, but not all pets are cats, right? We could talk like a parakeet might be out here somewhere, right? A parakeet is an example of a pet that doesn't fit inside that orange set. So we say the orange set is a subset of the green set because it's inside it. Same thing is true for the black set of dogs, right? Dogs, that's a subset of the set of pets because we're talking only about pets here. All dogs are pets, but not all pets are dogs. If we look inside the set of dogs, there are some other subsets, right? We could say that the blue set of small dogs is a subset of all dogs, right? Give me 1 to 5 so far. How we doing? Is this making sense? Okay. Another subset of the set of dogs might be dogs with curly hair. Okay. All dogs with curly hair are dogs, but not all dogs have curly hair, right? So there are, for example, Siberian Huskies would be out there somewhere, right? Because they're not small dogs and they're not curly dogs, right? What do we call the section that is in both the red and the blue sets? Anybody know what we call that when two sets collide? What do we call that section that's a part of both? Starts with an I. If you drove to school, you probably saw one of these this morning. Intersection? An intersection. There you go, right? So the intersection of the blue and the red sets is this football-shaped piece in the middle, right? That contains what kinds of dogs? Small and curly, right? So a subset of that intersection might be the set of all mini golden doodles, because all mini golden doodles are small dogs and they're also curly-haired dogs, right? And then inside that somewhere is the subset of the Oya family dog, which is Chuck. He's a little golden doodle. Okay, so that gives you an example of how things fit together in a Venn diagram. Okay, so now there's some other ways we can treat sets. So today is a lot of, there's really no algebra involved. None of this is going to be very mathy compared to stuff you've done in the past. It's really just all about defining, about vocabulary almost always, about some concepts and the vocabulary that goes with them. Because we have to know this stuff up front, so for the rest of the year we can use this to talk about math more precisely. It really helps in math if you have a good math vocabulary. Math is much, much less confusing. You understand what you're talking about, and there's not that, well, do we mean this or this? It's not so wishy-washy, right? So we want to spend a little time up front getting ourselves in that position where we can make things easier for the rest of the year. Okay, so we want to understand how we can write sets using notation. That's the next step. To do that, I want to remind you about something, that a set that you guys have talked about in the past, the set of integers. If you draw a number line, here's one way to think about the set of integers. Integers are all of the numbers on the number line that occur at the convenient places where you have the dash marks or the hash marks, right? Where do you put the hash marks on a number line? You don't put them by the numbers that require decimals or fractions to write. You put them by the convenient numbers that don't look like fractions, even though they actually are. We just don't write them that way. If I write 4 as a fraction, how would I write that as a fraction? Okay, good. We could always put a 1 on the bottom, but we just don't need to, so we don't, right? It's not necessary. So that's our set of integers. Okay, we're going to use that for a second. Here's a couple ways that we can write sets. So we're going to take this one set and we're going to write it two ways. The set right here that contains the set that contains the elements. Why is this doing this stuff? The set that contains the elements, one more time, contains the elements 1, 2, 3, and 4. What are elements? They're the things inside a set. Anything that's in a set is an element of that set. In this case, the elements are numbers. In this case, the elements were pets, dogs maybe, right? So one way we can write the set that I've described in that purple bubble is using roster form. That's what we can call it, roster form, or sometimes we just say set notation. Set notation looks like this. We're gonna use a set of set brackets. When we talk about set brackets, it's those things, the squiggly brackets. They're on a keyboard. It's not the parentheses or the square brackets. It's the other ones, right? They kind of look fancy, right? That means a set. So in this case, when we write roster form or set notation, all we do is we create a set with those fancy set brackets, and then inside, we're just going to list all of the elements in order, separated by commas. That's it. So here's one way to write that set that we described in the purple bubble. Real simple. That's it. Okay. You've seen stuff like that, I bet. Give me 1 to 5 on that. Does that look familiar? Okay. For the most part, maybe, right? If it's not already, it will be soon. Another way to do this is using set builder notation. Okay, so we can write the same set using set builder notation in a different way. It would look like this. Okay, that looks more complicated, doesn't it? It's a lot more words. Don't think that just because in this one example, set builder notation looked more complicated, that it's always that way. A lot of times, using this other type of notation, this set builder notation, will end up being way easier than using roster form. In fact, in some cases, you can't even write a set with roster form. It's just too hard to do. So what does this mean? Let's look at this blue example. There's a way that we say this in math. Using set builder notation, inside the set brackets, there are 3 separate parts. You start off with the very first thing you do in set builder notation is you have to say, well, what's the variable we're using to describe this? So in this case, it's an x, right? So the first thing we would say is the set of all x, and then this vertical line, it's called a conditional bar. In math, all you need to know is that always stands for the words such that. So we would literally read this as saying the set of all x such that x is an integer greater than or equal to 1 and less than or equal to 4. It's telling us how are we describing this, with what kind of a variable, and then using that variable, what's our definition? That's all it is. Okay? Okay, so eventually, we'll look at more examples of that. Eventually, we'll get to a point, fairly soon, where we'll be able to do a lot better than that. We'll be able to use more symbols and fewer words. This is a better way to write it, although right now it probably doesn't mean much. Okay, but that's within a few days, that's how we'll write that set. Okay, does that look scary? Okay, good. Don't let it look scary. Just because it has symbols, some people are saying, yeah, it looks a little scary. Just because it has some symbols that you're unfamiliar with, don't let that intimidate you. These symbols are your friends. This is going to allow you to write things in math without getting writer's cramp. You're not going to have to write so much stuff. All this says, I'll read it to you once. And then later on, this will make more sense. This just says the set of all x such that x is an element of the set of integers, or in other words, x is an integer, and x is greater than or equal to 1 and less than or equal to 4. That's it. Says the same thing, just in a way better, more mathematical, more precise, more efficient way. Okay. So now we kind of know how to deal with writing the sets. Now let's talk about them a little bit. So we've got this set of all the numbers that's the set of real numbers. We can start to break this up into pieces. So the set of real numbers we break up into two big pieces. There's two subsets that build up that big set of real numbers. One set is called the rational set of rational numbers, and the other one is the set of irrational numbers. And those are the subsets of real numbers. Every real number is either a rational number or an irrational number. You can't be both. Every real number is one or the other. Okay. Let's look at some definitions now, right? So the set of real numbers, how would somebody be really brave here. How could we say this using set builder notation? Here's a good definition, one possible definition, but a pretty good one of the set of real numbers. How do I say that? What's that stand for? How do I start it? Set of all x. What's that part? Such that, there you go, x corresponds to a point on the number line, right? The number line contains all numbers, all real numbers. So therefore, any x that can be written on the number line has to be a real number, right? That's a good way to describe it. Okay, so we know what real numbers are. Now let's distinguish between these smaller pieces, the subsets of real numbers. How would I say this one? It might be a little awkward, but just give it a try. How's that going to be? The set of, okay, good. The set of A over B, or all A over B. Set of A over B is fine. Such that, okay, good. A and B are integers, and B is, that symbol is not equal to, right? Anytime you take a symbol, a normal symbol, and you put a slash through it, you're just adding the word not to it, right? So instead of equal to, now it's not equal to, okay? Okay, what's that mean? The set of all A over B such that A and B are integers. So A and B are simple numbers, right? Easy to write, no fractions, no decimals. They don't look like fractions at least. And B is not equal to 0. Isn't that just saying fractions, right? If I take an integer divided by an integer, isn't that a fraction? Like if I did the integer 3 divided by the integer 2, that's 3 halves, right? That's the fraction 3 halves, okay? If I did the integer 4 divided by the integer 1, I get 4 over 1, which is a rational number, right? Make sense? Okay. What about this part? This is kind of important. We can't overlook that. How come we have to have that b is not equal to 0 part? I'll give you a hint. Look where the b is in that fraction. What do you think? Okay. We got two rules for real numbers that you guys have probably heard over and over again for years. One of them is for real numbers, you can't take a square root of what type of number? What was it? Negative, yeah, right? You can take square roots, like what's the square root of 4? 2. How come? Okay, because 2 squared is 4, right? What's the square root of 0? 0, because 0 squared is 0, right? 0 times 0 is 0. What's the square root of negative 4? There isn't one, right? Not a real number, because there's no number that you could square and get back a negative result. Anytime you square a real number, don't you always either get 0 or a positive answer, right? Okay, so that's one rule. Not important here. The other one is we can't ever divide by 0. Yeah, you can't divide by 0, can you? That doesn't make sense. That's not defined as a number. So we have to include that, okay? An easy way then to think about rational numbers is rational numbers are the real numbers that can be written as a fraction of integers, okay? And ratio means fraction. There's a strong hint here. The word ratio is literally in the word rational. So that's telling you fraction, okay? Irrational numbers, okay? How would we say this one? Set of irrational numbers is defined this way. It's the set of all x such that, okay, there we go. X is a real number and x is not a rational number. Isn't that just saying all the other ones then, right? All the real numbers that aren't rational, okay? Makes sense. All right, so for your notes, I included another little example. So, you know, when you look at your notes, you'll see that that's how we read that in case you forget, okay? Now let's focus on these. Let's go further. We divided real numbers up into the subsets of rational numbers and irrational numbers. For the purposes of this class, and really any high school class, we don't need to divide irrational numbers up beyond that. Rational numbers is that's a bucket of numbers that we're fine with. We don't need to be more specific. But the rational numbers, lots of times we like to divide that up into some smaller groups that are convenient for us to use. Sometimes we don't want to deal with fractions, right? Sometimes we only want to focus on the numbers that show up, for example, on the number line, on the hashes of a number line, okay? So if we look at the subsets of rational numbers, what do you think the biggest subset is? We already talked about it a little bit, right? The rational numbers are all the numbers that can be written as fractions. But what if we want to pick a simpler subset of that? What could that be? What are some subsets of rational numbers then? Right? I want numbers that are rational numbers, but they're specific types. What was it? Well, okay, we're going to talk about decimals, and that might play an important role. That's not what I'm looking for here. We're trying to get maybe simpler. We want to. What was it? Okay, irrational, that's the other set, right? Irrationals are different than rationals. Real numbers are broken up. I'm going to jump ahead for just a second. I'm going to jump up to this picture. I probably should have put this earlier. Here's a good way to represent the set of real numbers, right? I've got this big rectangle that represents all real numbers, and then I'm going to split that into a green part and a red part. Just ignore the circles for now, okay? Pretend they aren't there. I've got this green section that's the set of rational numbers, and the red section that's the set of irrational numbers, and combined those make the set of real numbers, right? So we want to know now what are going to be the subsets of the set of rational numbers that might be useful. Well, the first one we've already talked about. What do you think it is? Integers, yeah. The set of integers. Okay, so that's, again, now what are the integers? Those are just the numbers that show up as the dashes on a number line, right? Sometimes that's a convenient set. We use that a lot in math. We want to just only look at these types of numbers, so we restrict ourselves to the set of integers, okay? To write the set of integers, we used roster form here. We did not use set builder notation. That seems kind of weird though, right? Because think about what we did in this past example. We used roster form to describe a set that had 4 elements that I could write. Agreed? How many pieces are there in the set of integers? How many dashes are there on that number line? How many total dashes are there? Does the number line stop ever? So what do you think? Infinite. Yeah, there's an infinite number of hash marks if I go far enough in the negative direction or the positive direction, right? So that's kind of a weird concept that I'm going to use this set notation, not set builder notation, where I'm just going to list each of the elements. How am I going to write an infinite number of integers, right? How am I going to do that? I can't. You could never write an infinite number of anything because it never stops, right? You never finish. But I did. How did I do that? What about that made it okay to use set notation or roster form there? How does this stand for an infinite number of integers, even though I didn't write an infinite number? What do you think? Okay, yeah, look at this. Look at these three dots, right? What is this telling us? If we start in the middle at 0, integers is going to climb up by 1 from 0 to 1 to 2 to 3. And then what does this little dot, dot, dot mean? Yeah, etc. And so on and so forth, just following that pattern. We call that an ellipsis, and it just means keep going forever with that pattern. Same thing in the other direction. We start at 0, we're going to go down to -1, -2, -3, and so on. Keep going forever. So we can do it that way. Okay. There's our next subset of rational numbers. We're just going to restrict ourselves only to stuff like this. Give me an example of a rational number that is not an integer. Somebody throw one out. 2/3. There you go. Right? 2/3 is not in that set. It's not an integer, but it is rational. What's another one? What is it? 2.5. Yeah. Okay. Another one. That doesn't look like those, does it? Okay. So now vote with your thumbs here. True, false. True is up, false is down. True or false? All integers are rational numbers. Okay, I'm seeing a little bit of both. If you put your thumb down, how come? Give me an example of one that's not. Right? If it's a false statement, you got to give me at least one example that makes it false. There's one up here that I bet people are thinking of, though, a little bit. Which one of these numbers doesn't look like a fraction? 0, right? 0 doesn't, but it is. I'll show you why. 0 is a fraction. And you can convince yourselves here. I'll just help you. What is, oops, let me go down just a little bit here. Well, that's good. What is 0 divided by -25? 0. Okay. What's 0 divided by 1? 0 divided by anything other than 0 is 0, isn't it? Right? So look at that. We can always think of 0 as a fraction. 0 is the same thing as 0 divided by 1. So it actually does fit the pattern, right? So then how do we want to vote on this? True or false? All integers are rational numbers? True, right? All integers are rational numbers. True or false? All rational numbers are integers? False. There's some examples, right? That proves it. Okay, what do you think? Now, if we look at the set of integers, we'd break this up into parts, right? We've got the negative integers and the positive integers separated by 0. So what do you think if we want to look at a smaller set of integers, the next useful subset might be? Like which parts of, like, which integers might we discard and say, okay, we don't want to worry about those? The negatives, yeah. If we discard the negative integers, we get what's called the set of whole numbers, right? So those start at 0 and climb upwards forever, right? So they contain 0 and the positive integers. Now notice when I write the set of whole numbers down, I don't need an ellipsis on this side because it does stop at 0, doesn't it? It doesn't keep going. It stops at 0, but it keeps going in the positive direction. And then finally, the last set, if I'm just counting the number of oranges on the kitchen table, I don't need 0, do I? I just only need numbers starting at 1. And so I'd call those the natural numbers, and that's even a smaller subset. Okay? All right, so if we look at our diagram again then. Oh, and I put some stuff on here just for the notes. Just for the notes, it reminds you that the 3 dots is called an ellipsis, and it just means continuing that pattern. Members of a set are called elements. Just some stuff that, vocabulary, just so the stuff we talked about is in writing. So now, does this make sense? Okay. Does it make sense that inside this big green set of rational numbers, which contains all rational numbers, there's a smaller blue set that contains only the integers, right? Only the numbers that when written as a fraction have ones on the bottom. The hash is on a number line. And inside that set of integers would be just the 0 and the positive integers, right? And inside that set of whole numbers is just the positive integers, which we call the natural numbers. Okay, does it make sense that the number 2/3 has to go in the green section, right? Could it go in the blue section? Not an integer, so it can't, right? It's a rational number, but it's outside of the blue set. Does it make sense that the -8 has to go in the dark blue region, right? Because it is a rational number that is also an integer, but it's not a whole number. So it has to be outside of the light blue set. Agreed? And then 0 has to go in that light blue region because 0 is a rational number and an integer and a whole number, but it's not a natural number. Okay? In fact, 0 is the only number that goes in that light blue region, isn't it? Right? Okay, give me 1 to 5. How are we doing on this stuff? Okay? All right. All right. Now, don't panic when you see this. This is not for this year. This is for later on in math. As you go further and further in math, you can go a lot further with this idea. And you can draw diagrams that include completely other types of numbers. Like all the numbers we talked about today fit in this little section at the bottom. There are a bunch of other numbers that we haven't talked about yet that are called complex numbers, right? And we can divide these into different types of subsets too. And they have weird intersections. And it's, if you go further in math, you'll look at this stuff in more detail later. Okay, so let's get a little practice. All right, so I want to show you the flashcards that I built. I just tried this out, and it worked pretty well. So I built a set of flashcards for number sets in your textbook, and I haven't done this yet. Let's try matching. The practice is useful. The view all is just like, that's like traditional flashcards, right? It would be like, it'd be like you're holding a flashcard. On one side, it defines the set of rational numbers. On the other side, you'd have to explain what that is, define it. So what are rational numbers? What is that? What's our definition of rational numbers? Think back now. Come on. Contains the word ratio. What kind of numbers are rational numbers? Let's do this differently. Let's do the matching one. That'll be better. Okay. Okay. So gotta figure out which one is going with. You see anything up there that I can click on? So that's the one we're trying to match. That definition, or that word with it's the next one, isn't it? Everybody see that? Okay. That's the set of integers, isn't it? Okay, good. Those go. What about natural numbers? We got to define natural. Okay, let me make this a little smaller. There we go. Set of natural numbers. Is that what I had? Oh, it scrambled them. Yeah, it did. Okay, what's the set of natural numbers there? Positive. So that goes with that. Okay. And we already did, let's see, we did integers too, didn't we? Okay. Every time I click it, it just scrambles them again. Okay, what about irrational numbers? Okay, it's that one. Okay, how about whole numbers? And skip something. Okay, let's talk about decimals. And you guys have heard this before, I guarantee it. So rational numbers, when you write them as decimals, rational numbers always either repeat or terminate. Okay, what's that mean? Well, repeat means there's a pattern that just goes over and over again in the decimal. Terminate means it stops. So for example, 1/2 is a rational number. If I write that as a decimal, it terminates. It's 0.5 exactly. End of story, right? That's all we have to write. 5/4, if I write that as a decimal, is 1.25, done. Exactly, right? Those terminate. What about repeat? Okay, decimals that repeat, I could take the rational number 2/3. It's a fraction, so it's rational. If I write that as a decimal, well, it never stops, right? It's just the calculator would just say zero point 0.6 and so on and so forth, right? Forever. If your calculator had an infinitely big screen, the sixes would just go forever. Okay, well, we can't write that then because it would take forever to write it. Sometimes we'll do things like round. Like, what if we rounded that to 2 places? What would 2/3 be to 2 decimal places? 0.67, agreed? Is that equal to 2/3? No, it's rounded, so it's not. It's not exactly equal, is it? So if we want to write a repeating decimal exactly, we have to use a bar. Okay, what's that mean? Well, the repeating bar tells you what's the part of the pattern that keeps on going over and over and over again without end, repeats without end. So in this case, it's pretty simple. We just get every step we take, it's just a 6, right? So 0.6 repeating is how we would say that. Something like 1/11 is a little bit different. 1/11 repeats, but the pattern is a little more complex. It's 0.0909090909 forever. So what's the part that repeats? It's the 0.9, and so we need to put the bar over both the 0 and the 9. Okay, that making sense? You guys have done that before, right? Okay, so as decimals, rational numbers either repeat or terminate. Irrational numbers do neither one of those things. They never repeat and they never terminate. So like the classic example is pi. Pi is a decimal, just goes on forever. Never repeats, never terminates. It's just random, right? Same thing with any square root that persists. So if I have a square root of a number and when I simplify it, the square root does not go away, that is going to be an irrational number. Let's look at some examples. You got to be careful though, because sometimes, like you might see the square root of 36. Oh, square root, it's irrational. But is the square root of 36 irrational? What's it equal to? Yeah, it equals 6, right? So it is rational. That one's okay. We already talked about 0. 0 looks a little weird, but that's the same thing as 0/1, so it's rational. 1.2 is a terminating decimal, so I could write that as a fraction also, like 12/10, which I could even make smaller, 6/5. And then any mixed number, I can turn into an improper fraction, just a single fraction also, right? It's only numbers that have like symbols like pi in them or that have square roots of numbers that don't go away, right? Like the square root of 5 we're stuck with. There is no square root of 5, you can't simplify that. It's not like the square root of 36, right? If I have a number inside that's not a perfect square, I'm stuck with an irrational number, okay? So let's see, we did that. Okay, good place to end for today. When are we out of here? 5 after. Okay, yeah. So we'll wrap. There's a couple more things we'll do on Tuesday, and then you'll have the whole period to work on this. After that, let's just look at one more thing here real quick. Remind me real quick. If I wanted to write this green set using set builder notation, I could do something like this. How would I say that? What's the first part? Set of all x such that, there you go. Whoops, how come those didn't go away? There we go, okay. All right, so one other thing we'll just mention here. A set that contains nothing, contains no pieces or elements, is called the empty set, or sometimes we call it the null set. We'll call it the empty set. And it's symbolized one of two ways. You could write it as set brackets with nothing inside. That's one way to write the empty set. There's a set, but there's nothing in it. Or you can use a circle with a slash through it. That also means the empty set. So here's an example of something that is the empty set. The set of all x such that x is a month with 32 days. Okay, which months have 32 days? None of them, right? So that's the empty set. There are no months that fit those criteria, right? So that would be equal to either one of those ways we could say it's the empty set. Okay. Last thing, this is kind of like bonus level stuff here. Is that equal to the empty set, what I've got there? It sure seems like it, doesn't it? Okay, but it's actually not. This is really tricky. That's not the same thing as just the empty set because it's contained in a set. That's weird. So what this really is the set of the empty set. Okay? So it actually isn't an empty set. It's a set of something that is the empty set. Is the empty set nothing? No, it's not. It's something. It's the empty set. It just doesn't contain any elements is all, right? Does that make sense? That's kind of tricky. That's like I say, that's kind of bonus level stuff. Okay. All right, how do we do? Question. You can, but so what if you did something like here, let's represent this. Like if we did the empty set plus the set 1, 2 is equal to what? It's kind of like the set version of saying 0. Okay, does that make sense? Okay. How we doing? 1 to 5 on this stuff. We getting there a little bit? Okay, good. Am I going too slow? Okay. I'm starting slow because how many hours of math did you do every day over the summer? Okay, okay, not more than 2 or 3, so I'm going to go slow. Okay.